Okay, let's start. Welcome to afternoon session. And it's my pleasure to introduce Christian Böhning. He will give his second lecture in this conference about rigid, not infinitesimal surface of general type with ample canonical bundle. Yeah, thank you.
Yes, thank you very much. So yeah, the title of this talk already summarizes what I want to talk about. So I want to explain how to construct rigid, not infinitesimally rigid surfaces of general type with ample canonical bundle using line arrangements. And so these will be surfaces with Kuranishi spaces, a non-reduced point. Well, that's a recent project with Hans Christian von Bothmer and Roberto Pignatelli that we started actually in lockdown. So it's somehow an instance of lockdown mathematics. We just started it for the fun of it. And oh, sorry, I can't hear. So yes, okay, so fine. Right. So this is this exploits a very nice connection between synthetic projective geometry and combinatorial geometry of line arrangements in the plane, and the theory of algebraic surfaces. And that connection is certainly not new and has been used by many authors, so including Hirzebruch and Fantecchi, Pardini, Manetti, Catanese, Warwick, among others, to study properties of surfaces and vice versa, also deduce some synthetic properties of line arrangements. But so what we are doing is not just not just an incremental improvement over the previous work of those authors, but it's really something where we need some genuinely new ideas. And so, and I want to talk about the synthetic projective or the line arrangement part about half of the talk, and then the second half will be about applications to surfaces. All right, so right. So by the way, this so I'll say at the end how to put this work into context and how it relates to work by Warwick and by Karpovich-Milson and also by Bauer and Pignatelli, previous work by Bauer and Pignatelli. This also answers an old question by Kodaira and Morrow about deformation theory, by the way. So it's a bit orthogonal or skewed to the main topic of the conference, so I apologize for that, but it's fun, and also the construction, well, as many constructions do, makes use of unirational varieties or unirational variety or parametrization of that over the rationals at one point, but there's obviously not a very strong connection. So, so let me start with line arrangements and incidence schemes. So I should say that these surfaces are eventually constructed from some line arrangements, taking abelian covers of a suitable blow-up of P2 branched in a divisor constructed from such a line arrangement. So first definition is this, then simply, so a line arrangement, well, this is line arrangement is simply a finite set of lines in P2 over C. So everything is over complex numbers here, though I could also work over other algebraically closed base fields, certainly. So line arrangement, maybe not all characteristics, but yeah, basically all of them. So line arrangement L is a finite set of lines in P2, and so it's just like that, yes. And also in the following, I will always assume kill projectivities from the outset that so that these standard coordinate points, so I always assume that, so Q1, this point 1, 0, 0, and Q2, 0, 1, 0, Q3, 0, 0, 1, and Q4, 1, 1, 1 are among the intersection points of lines in the arrangement. I also want to introduce one other piece of terminology. So points in P through which 3 or more lines of the arrangement pass are called singular points of the arrangements. So, so points in P2 with 3 or more lines through, more lines of L passing through them. These are called singular points of L. Okay, so far so good. So of course one can say, well, nothing interesting has happened, but well, you will probably know that line arrangements still, although they look a bit dull at first sight, I mean, have some interesting properties. For example, if you consider line arrangements over R, then, well, you know that, well, then it is true, for example, that either all the lines of the arrangement pass through one point, or there is a point of P2 over R through which pass exactly 2 lines of the arrangement. That is just this dual statement of the Sylvester-Galai theorem. But for example, that is false if you look at arrangements that are not defined over R as the dual of, say, the Hesse configuration of inflection points of an elliptic curve together with the lines joining them shows. So that's well known. And also the theory of line arrangements, as I've already mentioned, has some very interesting connections to the theory of algebraic surfaces, as we will see. And really the flow of information goes both ways. So people in the past have also used the theory of algebraic surfaces to prove non-trivial combinatorial or synthetic project effects about line arrangements. For example, there's one theorem by Kelly, I think, that says that, well, if you have such a line arrangement in P2 over the complex numbers, and you don't have the case of a star of lines, so not all of the lines of the arrangement pass through a single point, and if moreover that line arrangement is free from double points, so there is no point here through which exactly 2 points of the arrangement pass, then there has to be at least a triple point. So there are statements of that nature, and so that particular statement apparently uses the Bogomolov-Miyaoka inequality for surfaces to get it. And there's no elementary combinatorial proof of known for that. So it's quite interesting, although these are very elementary objects. Now, I want to look at something else, namely incidence schemes associated to line arrangements. So those familiar work of Warwick may recognize that this is a similar punchline here we are pursuing, but it will be a little different afterwards. So I want to define what I call a generalized incidence scheme. And this is a slightly, longer definition, so I'll give an example after that. So I suppose that we are given in P2, well, first of all, points. So set of points, P, and I want to think of some of them, P1 up to Pm, as variable. So I'll just explain in a second what I mean by that. So I think of these as variable, and then of some other finite set of points here as fixed. These should be fixed. so a finite set. So of course a finite set of points, and then also a finite set of lines. We call it G, say, consisting again of well, n variable lines and some other set of fixed lines given at the outset. These are fixed. And then, well, of course, I can do the variable points and these variable lines, L1 up to Ln, as points in a product of projective spaces. So I call this P. So this will be P2 to the M times P2 dual to the N. And also I assume I'm given a relation. Yes, just some relation between points and lines. Some incidence relation corresponding to incidences. And then what I want to say and define, so I say a generalized incidence scheme. Associated to fixed data. Yes, I'm hearing some. Yes.
By relation, you just mean arbitrary subset? Or?
Yes. Yes. Arbitrary subset. Just arbitrary subset. Yes. Associated to fixed data, QI and MG. Well, is a closed subscheme, or is in this case the closed subscheme. I in this product of projective spaces defined by equations. Well, of course, for all R and N in this relation, I can view N as a linear form and R as a point in P2, and I just so demand that these incidences should hold by writing this equation, N of I equals 0. So in other words, so what is the point of these fixed data or fixed points and variable points and fixed lines and variable lines? Well, for example, if you have just one line and one point, so you look at the case of where M and N are both 1 and you're in P2 times P2 dual, then this incidence scheme could be defined by equations of by degree 1, 1, or 1, 0, or 0, 1, or they could even be completely redundant, depending on whether the point you're considering is fixed or variable, the line is fixed or variable, etc. Yes. So let me give you an example. So an example that we'll use to actually construct the surfaces afterwards. So here's an example. So here's example 3. Yes, so it has two parts, and now I have to figure out, no, that's probably not how it's done, huh? I don't know how this is changed. Just would like, maybe I want to use some color. That's the catch here. So what I want to draw the variable, the fixed lines and fixed points in red. So suppose I'm look at the case where I'm given 3 fixed points. So these are just the points 0, 0, 1, say, and 1, 0, 0, and 0, 1, 0. And then I look at, and I look at, say, 3 variable points and 3 variable lines. but these should be constrained, so the variable points should be constrained to lie on these fixed lines of the triangle in the way I'm drawing here. So this point somehow can move along this line, but it should lie on this line. It's constrained to lie on this line by an incidence relation. This can move here. Yes, and then I want 3 variable lines connecting the points like this. So I'm just looking at an inscribed triangle in this red triangle here. Oh, sorry, it's slightly skewy. So this is variable, and the red ones, oh, okay, the red ones are fixed. Okay, well, okay. Good. So this is then an example of a generalized incidence scheme in P2 to the third times P2 dual to the third. Yes, and it just, the points or the close points of it just correspond to inscribed green triangles in this fixed red triangle. And so that's one. So this is a positive dimensional incidence scheme, of course. And now I want to soup up this example slightly or modify it to something that I use afterwards. Again, same setup. So we have this red triangle with these points, same points. I'm also looking at 3, this doesn't work very well, at 3 variable points lying on the sides of this red triangle and 3 variable lines joining them so that I get an triangle. But now I want to rigidify the situation by additionally demanding that, well, these green lines should pass through 3 further points, P, Q, and R, that are fixed. P, Q, and R are fixed, are given somewhere here in P2, and I demand that the green lines pass through them as drawn. Yes, and so then I get again an incidence scheme in, of course, P2 cubed times P2 dual cubed, and but now so this is what we call, what I want to call a PQR scheme, the setup, and just for the purpose of this talk. And it turns out if you do the computation, or if you, well, you can also see it abstractly, but you can just compute that in general. Such a PQR scheme consists of 2 reduced points, but it can happen that in special cases you get a non-reduced, a double point, just a double point in the FN line. So in general, such a PQR scheme consists of 2 reduced points. And for special values of PQR, one can get double point. So just spec, yeah, just double point here. And so there are generalized incidence schemes that are non-reduced point, but I can't use generalized incidence schemes to construct the surfaces the way I want. I need a special type of incidence scheme, and that causes, well, that causes some complications in the construction, or that is where one needs to find some ways to, or need some clever ways to fix this. So what I want to define next is line configuration So what I want is, I don't want a non-reduced generalized incidence scheme. I want an incidence scheme that comes from a line configuration. So or line configuration or line arrangement L defines, if I'm given an arrangement of lines, then this defines in a natural way a generalized incidence scheme which is associated to fixed data, just the coordinate points, Q1 up to Q4. And I want to call such a generalized incidence scheme that is associated just these 4 points as fixed data, simply an incidence scheme without any other attributes. An incidence scheme. And so how does that work? I mean, in the obvious way. So somehow the singular points, so the singular points of the arrangements, or to each singular point of the arrangement, other than possibly Q1 up to Q4, I introduce a variable point. Yes, and to the lines of a line of the arrangement, I introduce a variable line, and then I impose the incidences that I am given, that are given by the line arrangement, and that's it. So that's the obvious way in which a line arrangement defines a generalized incidence scheme associated to these fixed data Q1 up to Q4. And now I want to tell you, so I'll probably just sketch the proof, because, well, the proof is, depending on the way you look at it, either trivial, but it's a bit lengthy, and you have to have even more notation to say what it is precisely. So I want to say that there are incidence schemes. There are incidence schemes yeah, so here I should say, so this incidence scheme defined by the line arrangement, let me call that I of L. I say that there are incidence schemes of form I of L that are isomorphic to a PQR scheme, which is a non-reduced point. Yes, and yes, what is the idea of the proof? I mean, the rough idea is this. Well, I mean, first of all, one observation is that if you want a generalized incidence scheme, and there is a variable line in it which is required to pass through two fixed points, then you can pass to an isomorphic incidence, generalized incidence scheme, where this line gets replaced by a fixed line. And similarly for points. So, and you can use this then to construct an incidence scheme of this form, I of L, isomorphic to a PQR scheme, which is a non-reduced point. PQR scheme, certain values of PQ and R, yes. And then you need to construct PQR successively, starting from the points Q1, Q2, Q3, Q4, by a succession of steps of the following form. So basically call a point, say, constructible in 0 steps if it's Q1, Q2, Q3, or Q4, then call a line constructible in n steps if it if it joins 2 points that are constructible in n-1 steps, and call well, a point constructible in n steps if it's an intersection point of two lines constructible in n steps. So you successively enlarge your bag of, or your collection of points and lines starting from these 4 coordinate points, and you want to get, or you want to have that PQR, these 3 points that give you your non-reduced PQR scheme, are constructible in say n steps, but these green lines of the PQR scheme contain no other points that have been constructed up to that step n. So they contain no other points constructible in n-1 steps or fewer steps. So then you can get that. So and to get to that scenario, you need to choose PQR carefully at the outset, and where they must be a little more complicated than the simplest examples you can think of, and that's where it's important to find PQR of reasonably large height, so the complexity of their coordinates, where they must not be too simple. So we find suitable PQR that do the jobs, and then so we constructed one example. So one example of such a line arrangement. And maybe for the following, let me call it L hard. Okay, so that's the line arrangement that is that we want to work with. In our case, this has 34 lines and it has 51 singular points. Okay, so we can construct such line arrangements. And so now what do we do with them? So once we have such a line arrangement, we can construct a surface from it. So this is part 2 about algebraic surfaces. So what I do is, of course, the obvious thing. So I now assume I'm given a line arrangement. L, having lines say L1 up to Ln, and so L will be this L hard always in the sequel, and so it has singular points, so singular points P1 up to Pm, and then I blow up my P2 in the singular point, and I just look at, so I blow up, so blow up, let me just blow up P2 in the singular points, get this blow up here, get this surface, which is the blow up, and then B, so this will be my branch divisor for the surface I'm constructing. So this should be the union of the strict transforms of the Li, say Li bar, and the exceptional divisors. This is now some simple normal crossing divisor there on my S. Yes, and now we look for so we want to construct so we want to construct an abelian cover of S. And so what we really want to construct, a smooth and also totally ramified, really. So it should infect it non-trivially over some metal cover of S. So we want to construct a smooth, totally right Galois cover S tilde of S with some elementary abelian P group as group of deck transformations. So with group G, so some Z modulo P to the R. Actually, in our example later, P will be 7 and R will be 4. But other examples are possible, but that was the easiest we could come up with. So, and with branch divisor B, so this is just a finite flat map, and we have a faithful action of G on S tilde, and well, S is just the quotient for that action. And we want to arrange things that, right, and we want to arrange things such that, well, the Kuranishi space of S tilde, so this is the Kuranishi space of S tilde, is a germ of an analytic space for me. Well, you could also think about it differently, formally. Kuranishi space. Yes?
Sorry, do you fix some monodromy data? I mean,
I'll tell you how we construct the covering. I'm just saying this is the goal. I'll just tell you in a minute how we construct it. Yeah.
Okay.
Yeah. So this is different. Of course, it is not clear how to do it. Yeah. Right.
Okay.
But yeah, such that such that the Kuranishi space of this S tilde is isomorphic to the incidence scheme of our line configuration. So how do we do it? So how do we construct this? So we construct right. So we construct first of all the cover S tilde using, well, a method by Pardini. So this is a very classical method by Rita Pardini that lots of people afterwards have used. So Catanese, Manet, Fantecchi, etc. So and she starts from so-called building data. Also Varkil does that. So building data for such a cover. So what are these? So well, essentially you have to give yourself two maps D. So not homomorphisms or anything, just two maps from D from the D, this elementary abelian group, to the effective divisors on S. So with image your branch divisor or image B, yeah, ones of P, that you want to construct your cover with. And you have another map L, so L for line bundles, that goes from a group of characters here to the PK group of S. And you want this to do, you want to construct these such that, well, I mean, this D associates to group element G, divisor DG, and to chi, you associate L chi, a line bundle, such that how you want to associate to the trivial element in your group just the zero divisor, and well, you want that P times L chi, so in pic of your surface, is just a sum over, and then you write here O G in G, and here you pair chi with and DG. So you need this congruence condition, kind of congruence condition, to build the cover. And this thing here is just well, it's an integer in the set from 0 to p minus 1, lifting the natural pairing between characters, and so lifting this number here in z modulo pz to z. Yes, so you need this, and well, I mean, you need more eventually. So for the cover to be smooth, well, there are
So
there is a criterion for
your
the
characters take values not in C star, or you identify p-th roots of unity?
I identify, yeah, I choose p-th roots of unity, yeah,
Okay.
yeah, at the outset, yes, yes, right, and right, and so you also want that, yes, so for the cover to be smooth, you want that whenever two non-zero DGs intersect in a point, then the corresponding labels here, these G's, are linearly, over ZP, linearly dependent in the group. So that ensures smoothness, and you also want that the G's generate. So the G's that occur as labels for non-zero DGs generate the whole group G. So this ensures that, so this is totally ramified. So you can think of it as follows. I mean, somehow if you start out with a cover, then you can always, well, look at the direct image of S tilde, and that splits into the direct sum of these such character sheaves, yes. And those are your L chi, yes. And then on the other hand, so how do you get these labels for the DGs? Well, you start with some irreducible component of the ramification divisor upstairs, and you look at its inertia group, so the group of elements in G that fix that component pointwise, and this turns out to be cyclic. So this has a faithful representation on, well, the cotangent space, you could say, of the generic point of that component. And so it's cyclic, and it acts on that space via some character. So to each such component, you associate some cyclic subgroup of G together with a distinguished element, say the preimage of 1 in Z mod P under this character homomorphism. And this is your label of the irreducible component of the ramification divisor upstairs. And you can do that as a label of the branch, the corresponding component of the branch divisor downstairs, because your group is abelian. So all the labels really of different preimages of this DG, they are the same. So this is somehow how you can, if you're already given a cover, then you can construct such data fulfilling all these requirements. And conversely, from these data, which are, well, algebraic or more combinatorial in nature, you can reconstruct a cover of that type. So that is Pardini's theorem.
Can you write down multiplication explicitly?
Yes, you can, but I would want to avoid it. So that's the main point. That's the main point, yeah, to recover the ring structure. Yes, that's precisely the main point. Yes, so that's why this congruence condition is imposed here. Yeah. But so we need to find such data to get a cover, but then we have some cover, right? But the cover doesn't yet have the property that its Kuranishi space, I mean, it need not have this property that the Kuranishi space of S tilde is now, has anything to do with that incidence scheme of the line arrangement we started with. So, and for that, we have to remark two further things. So we remark first that this incidence scheme of the line arrangement is naturally isomorphic to, well, the deformations, let me say, of the pair, so the Kuranishi space, so the deformation space, parametrizing deformations of S, let me say, together with deformations of the closed embeddings of all irreducible components of B, which are smooth, just smooth rational curves. Also of closed embeddings of, say, all irreducible components of B. So in other words, it's a fiber product of some relative Hilbert schemes of the Kuranishi family of S, corresponding to the components of B. So this is just essentially Kodaira's stability, or Kodaira's theorem on stability of -1 curves. Formations, you can deform them, they remain -1 curves, and you can blow them down in the family. And yeah, so this is one point. The other point is that, so this is the hardest point really, and that is something that has well, caused us a lot of trouble, but well, depending, I can tell you more if you ask me at the end, if you want to, but this is very technical. Let me here just say we use a generalization. We use a generalization of a method due to Manetti to prove that, well, under certain conditions, of course, so under certain cohomological vanishing conditions, etc., the deformations, this A, B, are the same as are isomorphic to the Kuranishi space of S tilde. So, so in other words, all deformations of the cover come from deformations of S together with the deformations of the irreducible components of this B. And this is something that had already been shown also under different conditions by Fantecchi and, yes?
So
Sorry.
this is somehow independent on your choice of building data?
No, it depends. We have to choose everything, but we have to choose the building data so that they satisfy all of this.
Yeah,
yes.
But in your isomorphism, there is no building data anywhere. Yeah.
No. Yes. Well, maybe I didn't say it correctly. I say we have to choose. We have to construct the cover at the beginning, so that, well, first of all, it is a cover of the desired type. It is smooth, a totally ramified Galois cover with a certain group G. So we choose, well, eventually for us, it's this group Z07 to the fourth, and such that we also have this isomorphism in the end. And to have this isomorphism, we require even more restrictions on the building data. Yes, so we have to choose the building data so that, moreover, we can satisfy certain cohomological vanishing conditions and other conditions that are generalizations of some conditions due to Manetti that I won't write down. I can write down if you force me to, but it's a long list. It's a long list.
I just wanted to understand.
And so the data we construct has to satisfy all conditions.
So what you mean is that for some choice of building data, there is an isomorphism like this, right?
Yes.
Okay, thanks.
For a careful choice of building data, there is an isomorphism like this. Yes. And the catch is how what Manetti and Fantecchi Pardini show is morely if the building data is what they call ample enough, which means that the L chi, well, are, for example, if they are ample and ample enough, then all of this is fine. However, we can't arrange the things so that our chi are ample enough to satisfy the conditions that Fantecchi, Pardini, Manetti set down, or that they prove are sufficient to ensure this. So we need to prove a generalization first, and so kind of exhibit weaker conditions, and those we can satisfy. Yeah, in particular, so some vanishing conditions that Manetti assumed cannot be satisfied, and we need to replace these, asking for, well, injectivity of certain maps instead. And we have to compute the maps explicitly. And so this gets complicated. Yeah, or that's the most complicated part of the whole work, actually. So, so once we've done this, so let me maybe say what, and then let me try to put this into perspective in the remaining 10 minutes or so. So once we can accomplish all this, we get the main theorem, so that so there exist surfaces as tilde of general type. So we also have to check that they have general type with, well, with K ample, but this is then a very, well, this is an easy computation using the Nakasan criterion, and Kuranishi space a non-reduced point. And actually this double point, so a non-reduced point, isomorphic to this, well, just standard double point. Yes, and right, and maybe let me also tell you what these surfaces are. So we found suitable building data, writing down all these different conditions, some of which I've not told you. But then we computed at least K square and chi to do some sanity checks. And so for the simplest surface, we found K square is 1,260,966, and chi is, if I wrote this down correctly, 151,802. And so what I just want to say is that the ratio K squared divided by K is approximately 8.3, which is good because it's between 5 and 9. And so, I mean, K squared should be less than 9 chi, so that the surface can even exist and satisfy the Bothmer inequality. And also, on the other hand, the number of moduli is somehow bounded from below by 10 chi minus 2k squared. So this number should be non-positive. So this ratio should also be greater than or equal to 5. So it's actually in the permissible range. At least, so that shows that at some sanity check, so that at least this is consistent. And yeah, let me try to put this into perspective. So why is it interesting, and what was known before? So of course it's so we weren't the first ones to construct such surfaces. Such manifolds that are rigid, but not infinitesimally rigid, were first constructed by Ingrid Bauer and Roberto Pignatelli in 2018. And construct surfaces well, of general type, so that are rigid, but not infinitesimally rigid. But for those, K is not ample. K is not ample, and indeed the canonical models of them are infinitesimally rigid. So, so their construction is is different. So they start from some infinitesimally rigid nodal surfaces, and then they resolve those to get a bunch of -2 curves. And the presence of these -2 curves in these cases is precisely responsible for the fact that the Kuranishi spaces for those examples, for the resolutions, become non-reduced points. So they use a theory of, or theorem by Burns and Wahl to relate deformations of a canonical model, which is singular nodal in that case, and the deformations of the singularities and the deformations of a neighborhood of the exceptional locus of a resolution of the singularities with the deformation of the resolution surface. Actually, that what I just said, that forms some Cartesian diagram, and then you get the Kuranishi space of that desingularized surface is non-reduced. So here, so you see that somehow. So in which way is our example an improvement over theirs? Well, one may wonder whether this presence of -2 curves and this fact that one resolved an infinitesimally rigid canonical model is the only way such surfaces or such manifolds can arise. So we wanted to find examples where the canonical models are themselves rigid but not infinitesimally rigid, which is the case in our examples, because this S tilde, of course, is the canonical model in this example. So we wanted to find examples where the fact that that these deformation spaces are rigid but not infinitesimally rigid has some more modular reason. Yeah, and let me just say that this answers an old question by Kodara and Morrow, so who in around 1970 asked whether there were examples of rigid but not infinitesimally rigid compact complex manifolds, any such examples. And to the best of my knowledge, so Bauer and Pignatelli were the first who in 2018 exhibited examples of such compact complex manifolds in the form of such surfaces, and higher dimensional examples, say taking products with some other rigid manifold. But yes, so our examples are the first that have rigid but not infinitesimally rigid canonical models as well. And yeah, so something else I want to say. So you may wonder, so how this relates to work by Warwick, who 2006 looked at these phenomena, summarized under the heading Murphy's Law for moduli spaces. Well, Warwick, I could write here, he proved a stable version of this result. So he proves that, well, let me say it maybe precisely. What he looks at are singularity types of pointed schemes. So so he looks at pointed schemes, and then he looks at the modulo and equivalence relation. So namely, if you have a smooth morphism from x comma p to y comma q, then you consider those two as giving the same singularity type, and you take the equivalence on pointed schemes. You take the equivalence relation generated on pointed schemes by these elementary equivalences. So in other words, Warwick only looks at singularities up to addition of smooth parameters, or subtraction of smooth parameters, up to smooth parameters. And well, then he proved lots of theorems, for example, that every well, every singularity type realized by some scheme of finite type over spec Z occurs on some moduli space of surfaces of general type, even with very ample canonical. But of course, what this means is that you always have to take into account the possibility that you may have to add some number of parameters. So you never get really rigid examples if you want to, if you do what Varkey does. Yes, because you can never be sure that, well, you may have to add some parameters for his methods to work, and you can't get down to dimension 0 in this way. Actually, what he bases his approach on is Nyoff's universality theorem, which says somehow every singularity type that realized by some scheme of finite type over spec Z can be found on some incidence scheme. Well, to prove this, you really have to allow for the addition of extra parameters. And there's also a non-stable version of this due to Kapovic-Milson, but on the other hand, so we first thought we could use their work to immediately get this conclusion. But if you think about it, they look at a slightly different moduli problem. So they look at what they call finite-based realizations of abstract incidence schemes of points and lines. And these realizations need not be injective. So, so points could coincide and so different lines, abstract lines could map to the same line. And so we can't use that for the construction of our surfaces. So that's a subtle point. So maybe that's hard to get across, but so our result doesn't really follow from their work either in any way. So let me maybe just say what is still open is whether in our example also the Gieseker moduli space is a non-reduced point. Is the Gieseker moduli space in our example also a non-reduced point. So we know that the Kuranishi space is a non-reduced point, so we cannot really guarantee that this group of deck transformations G is the entire automorphism group of our surface. Could be larger. But there are conditions that guarantee that, but they are not satisfied in our example. But they are only sufficient conditions. So maybe we can prove it at some point. But yeah, that's the open. Yeah, so let me stop here.
Thank you very much. So is there any question? So can I ask you a very naive question? So your ratio between the k-scale and the chi is quite high, I think 8.3. So yes. As you know, this fake projective plane is always 9. And so what I mean, is there some rigidity has something to do with this ratio? So when this ratio is high, then the surface has tendency to be,
Yeah, because you see the number of moduli is simply bounded. So it definitely has to be higher than 5 for it to have any chance to be rigid. Because the number of moduli is bounded from below by 10 chi minus 2k squared. So this should be non-positive. Yes. But then in some sense, yeah, one could say intuitively, if it's higher, it gets better and better. Yes. But of course, you could always, I mean, usually you will find examples that are actually infinitesimally rigid. So very frequently, it's not very hard to construct examples where the Kuranishi space is some reduced point. But I mean, here actually the difficulty comes from the fact that we want to have examples where it's a non-reduced point. So somehow you can infinitesimally wiggle the surface, but not, but not actually. Yes.
Is there any example that you have this ratio greater than 8, but still non-rigid? Is there any such example?
I wouldn't know. No, I don't know. I would have to think about it. I mean, probably, yeah, I think there could be. But
in this ratio is 8, then there are many surface with moduli, high, big dimensional moduli, but greater than 8, I'm not sure. Anyway.
Yeah. Well, I don't know. I would have to think about it. I mean, it could be possible, but I can't answer it. So, on the spur of the moment, unfortunately.
I see. So, other question? Okay. If not, let's thanks to our speaker again.
Yep.